So let's see the introduction to artificial intelligence, AI, machine learning, deep learning, and generative AI. So the buzzing term right now in any industry, be it healthcare or finance or retail or manufacturing or technical or any non-technical domain, it is AI. So everywhere we have been hearing the term AI, artificial intelligence. So AI is a broad term, so everything together is called artificial intelligence. So what is artificial intelligence? In layman terms, artificial intelligence means trying to mimic humans. So as humans we have intelligence. So how do we mimic humans? For example, let's say you have a kid and you want to teach the kid fruit names. So how do we teach the kid to learn a fruit name? We will teach the kid by showing an apple or orange and teach that the fruit name is apple or orange, and we will also teach the color of apple is red or color of orange is orange color, right? So when we repeatedly train or teach the same thing to the kid, it registers in their brain. And we know the human brain has neurons, right? So when we show the similar image of the fruit, either apple or orange, to the kid multiple times, their brain finds the image pattern, that is neurons in the brain understands the shape or color of apple or orange. So this process is called training. That is, you are showing multiple fruit images to the kid as input and teaching them the output. So that is the label. The label is the output. That is the color of the fruit or shape of the fruit. So input is apple or orange image and the output is either color of the fruit or the shape of the fruit. So once the kid is trained, the kid understands the pattern. So similarly, the machine learning model understands the pattern when we train the model with enormous amounts of data. That is, the data could be gigabytes or petabytes of data. So once the model is trained, then we will give a completely new image and the model will be able to predict the features of the image, just like how a kid can identify the fruit image. So artificial intelligence AI is nothing but mimicking a human. So can we understand how the human brain is working, and can we train a machine or model with the same information so that a model can do the same thing that a human can do? But how can we train a model? By using mathematics. It's all pattern finding. Therefore, AI means pattern finding. That is either from the structured data, that is your tabular data, or unstructured data. Unstructured data means either text or image or audio or video data, and the intent is to be able to identify the pattern. So the objective of artificial intelligence AI is to understand the patterns from the data, similar to how our brain is working. So that is the objective of AI. So if you notice here, inside artificial intelligence AI we have machine learning, ML, and inside machine learning we have deep learning, DL, and inside deep learning we have generative AI. So generative AI is one of the subject in deep learning. So this is where we will try to spend majority of our time and try to understand what is generative AI and what are these large language models inside this generative AI. So artificial intelligence has information retrieval, IR, machine learning or NLP, natural language processing, CV, computer vision, soft computing, fuzzy logic, etc. So artificial intelligence contains several topics inside it. Now let's see how do we train a model, right? How can we give intelligence to model, machine learning? So how can we give the intelligence to these machines, like logical thinking or mathematical calculations or strategic decision making, etc., right? So that is the whole objective of machine learning. So we need to be able to train a model. So how can we train a model? So first thing is we need to collect the data, right? So first data collection, and the next thing is clean the data. So that is clean all the garbage data, and then feature engineering, that is build the model and then train the model, and then evaluation, that is validate or test the model, and then deploy the model, and then monitor. So this is the complete life cycle of a machine learning model. And majority of the time we spend on data collection, cleaning, or model training, and validation, that is evaluation or deployment. These shouldn't take much time, and iteratively we will do all these tasks until the model predicts accurate results, that is until the model finds the patterns. And we have big companies like Google, Microsoft, Meta, right? So these companies, they automated this entire process. They have collected all the publicly available data present on the internet, be it Wikipedia data or from books or any public data that is available on the internet. They have collected the data, they cleaned the data, they trained the model and provided us with a pre-trained model. For example, we have ChatGPT, Gemini, Olama, Grok, etc. So we have different pre-trained models already available, and all the problems that we can solve using artificial intelligence are divided into three types. So these are different types of machine learning algorithms. We have supervised learning, unsupervised learning, and also semi-supervised learning. So what is supervised learning? This one uses labeled datasets where the input and the corresponding output or target are known. So we already know what is input, what is output. And in case of unsupervised learning, this one uses unlabeled datasets where the input data is provided without any corresponding output or target. And the third one is semi-supervised. So this uses the combination of both labeled and unlabeled data. So what is supervised learning, right? So supervised learning is exact replica of our human brain. That is like how human thinks, right? For example, when we were born, right, we didn't know anything, like we don't know who our mom or dad or anything else, right? But someone has taught you and eventually we learned it. We learn through examples, right? For example, face recognitions. You have seen your mom or dad multiple times. So as a kid, we were able to understand who our mom or dad is and we were able to recognize them. So to identify a person or face recognition, you need a kid to identify the people. For that, you need to provide the input as an image of that person, and the output is nothing but the person name, that is either your mom or dad. And you need to train with multiple images. For example, mom having a long hair or short hair, or mom with specs or without specs, or with mask or without mask, or with different color dresses, right? So the images are not constant, right? The image has different variation, but the kid will eventually understand who is mom or who is dad, right? So deep learning means you need to train with a lot of data, that is either gigabytes or terabytes or petabytes of data, right? So this is called supervised learning. So we are training the model with both input, that is x, and output, that is y. So the model will try to understand the relationship between x and y, that is input and output. So this is called pattern finding, right? Once the model is trained with huge amounts of data, and once the model understands the pattern, that is the relationship between x and y, then given x with any new data, right, the model will be able to predict y. So given x, predict y. This is nothing but supervised learning. And the objective of supervised learning is given x, predict y. And how the model can identify, right? Because we are training the model with huge amounts of data. If this is x, then this is y. This is x, then this is y. So eventually the model will understand the pattern or relationship between x and y, and whenever we give a new x, it will predict y. So which is nothing but a pattern finding between input and output. So training the model means give a lot of examples so the model will understand the pattern between input and output. So this is called pattern finding. So this is the whole story of deep learning. And the next one is generative AI, generative artificial intelligence. So this is a subsection of deep learning, as you can see in the diagram. So generative AI is nothing but a pre-trained model. meaning this pre-trained model has some generic intelligence because the model has been trained with publicly available data. And the objective of generative AI is generating. That is, the model can generate either text or video or images or audio, right? So inside generative AI, we have large language model LLM, right? So we have models that generate either text or models that can generate vision, that is images, or we also have multimodal, means both image and text. So by using these pre-trained large language models, we can perform generic tasks like text to audio conversion or sentiment analysis or conversion from one language to another. All these tasks can be performed by using these pre-trained large language models. And these large language models can be either open source or paid models. If it is a paid model, then we need to make an API call to use the model. Whereas if it is an open source, then you can download the model to your machine and use it. So these models are like plug and play, that is model as a service. So before these pre-trained models were released, to build a model from scratch, it used to take a lot of time. But with the pre-trained model, the task can be done easily. For example, if you want to build a chatbot for a domain specific project, instead of you building from scratch, take this pre-trained available model, give your domain specific data as input, right? Which is nothing but fine tuning or RAG, retrieval augmented generation. We will talk about RAG in detail in the coming lessons because the model is already pre-trained, so the model already has some generic intelligence and you are fine tuning with your domain specific data, so the model will eventually be able to accurately predict the results, right? And when it comes to open source pre-trained models, we have Olama, that is the most famous, and there are like 10 lakh open source models already available in Hugging Face, and we have a separate lesson for Hugging Face. I will talk more about it in the coming lectures. And we also have paid pre-trained models, right? For example, ChatGPT or Claude, Anthropic, etc., right? So you do not have to build the model from scratch. The real challenge in real time is if the model will not be able to predict the accurate results, that is called hallucination, even after training the model with your domain specific data. That is why you need to be able to debug the model or improve the model, right? So that's the real challenge in real time. And the data that we will be training a model can be of three types. We have structured data, semi-structured data, unstructured data. So structured data means it can be your tabular data, that is RDBMS data. We mostly use either machine learning or deep learning when the data is structured data. And for semi-structured data, for example, CSV files, XML or Excel, JSON files, etc. For semi-structured data also, we mostly use either machine learning or deep learning. And for unstructured data, for example, images, audio, videos are nothing but frames, right? So frames are nothing but images or text, etc. And for unstructured data, we mostly use generative AI models, which internally uses deep learning. That is, these are pre-trained models. So machines can identify only when the data has any pattern. If the data is random, the model will not be able to identify the pattern. So this data plays a crucial role when training a model, right? So after feeding so many images to a model, it will be able to eventually identify the pattern, and this entire process can be automated using generative AI. So they have automated this process. They've collected the data, they cleaned the data, they built the model, they trained the model, evaluated and deployed, and these are nothing but large language models. These are pre-trained models. So generative AI uses transformers or GAN, that is generative adversarial network, VAE, variational autoencoder algorithms. We will discuss the architecture behind these large language models in the coming lectures. But with this, I hope you got a decent understanding on the terms like AI, artificial intelligence, ML, machine learning, DL, deep learning, generative AI, or LLM, large language models. So we will deep dive in the coming lectures. Alright, thank you. So in this lecture, let's see a brief history of artificial intelligence with deep learning. So if you notice here, you can see perceptron is not new, right? So it was there in 1957 itself, but you can see from 2010 onwards, there is an exponential growth, and we solved a problem called vanishing gradient descent. That is when the deep learning became so popular around this time, and transformer was introduced by Google in 2017. So that's when the growth started exponentially, because without transformer there is nothing. So using transformers, they started creating these small language models or large language models like these GPTs, right? So that is the brief history of AI. So you can see the growth from the birth of AI to the perceptron and CNN, convolutional neural network, and GAN networks, transformers, and ChatGPTs, right? So this is the brief history of artificial intelligence, and we will discuss the architecture behind these large language models, that is transformer, in detail in the coming lectures. All right, thank you. In this lecture, let's talk about transformer architecture. Like I said in previous lectures, we already have a lot of pre-trained models and you do not need to build anything from scratch, right? But knowing the transformer architecture will help you build any model from scratch in case if you need to build, or it can help you to understand how the pre-trained model works, right? So why are we learning transformer? So if you notice in this diagram, AI, artificial intelligence, this is the broad term. So the objective of artificial intelligence is to find patterns from the given data. So we are trying to make the machine so intelligent that it can behave like a human. So how do we achieve that? How do we give intelligence to a machine? So to achieve this, we have machine learning, deep learning, NLP, natural language processing, generative models, right? So we have different mechanisms available to make the machine intelligent like a human. And the objective of generative models is to generate something, as the name suggests. We use generative models mostly on the unstructured data. The model can generate either text or image, or text or image, right? That's a multimodal combination. So the main algorithms inside these generative models are VAE, that is variational autoencoder, and the second one is GAN networks, that is generative adversarial network, and the third one is transformer, right? Those are the architectures behind these large language models. So why are we learning transformer, right? So we will know how these large language models are built and the architecture behind these LLM, that is GPTs or any other pre-trained models, right? In generative models, 90% of the models are built on top of the transformer architecture, right? And I also want to clarify here, not all the models are built using transformer architecture, right? For example, deepfake video generation is built on top of GAN network. But majority of the generative AI models are built on top of the transformer architecture. So that is why we are trying to understand transformer architecture, so you can understand how these large language models work internally, right? And in 2017, Google released a paper and the architecture was very well explained. And before that, Google released a model called BERT. BERT is bidirectional encoder representations from transformers. And this was the old model. But as you know, we have GPT-1, GPT-2, GPT-3, GPT-4. All these GPTs, they are built on top of transformer architecture. So transformer is a part of generative models, which is part of neural networks, and which is part of machine learning, and which is part of artificial intelligence. Now let's see what is a transformer. And you can see here, this is the architecture of the transformer, and we are learning both encoder and decoder. but GPT is only decoder. Some models are only encoder based and some models are only decoder based. For example, BERT, right? BERT is only encoder based model, whereas GPT is generative pre-trained transformer. GPT is decoder based model. But let's learn both encoder and decoder model so you will understand the entire transformer architecture. So first let's start with encoder and then we will move on to decoder, right? So this is the encoder piece, and as I said, BERT is encoder model. Assume you are using BERT model as it is an encoder based model, that is a transformer based language model, and BERT uses a vocabulary of 30,522 tokens. These are unique tokens or words, and they achieved through word piece tokenization, which breaks words into subword units. But these 30,522 unique tokens or words are the most common English words. So as I said, these are only the most common words. We may have happiness in the list, but the model is intelligent enough to understand the opposite word of happiness is unhappiness. Even if unhappiness is not present in this 30,522 tokens, the model is intelligent enough to understand the opposite word of happiness is unhappiness, right? And as you can see in the diagram, the first thing that we are doing here is we are providing an input to the model. Here in our example, we are considering BERT model, which has a vocabulary of 30,522 unique words or tokens, right? So first we are providing the input, and this input will be converted to input embeddings, right? So assume this is the input to the transformer. We are giving this is a generative AI course. So assume this is the input sequence that we are providing to our BERT model, and then this is just one sentence, but in real time we may have several sentences as well, right? I just took only one sentence as an example so we can understand the architecture behind the transformer. Okay, so once we provide this input to the model, then the next step is tokenization, right? So that is, it will convert the input into tokens. So our input is, this is a generative AI course, and it will convert into tokens, that is, this is a generative AI course, right? We have 6 tokens, and once the tokenization is done, the next step is token IDs. So we are trying to represent each token with a token ID. This token ID is nothing but the position of the word or token in the entire vocabulary of 30,522 unique words, right? For example, let's consider the word this, right? So this may be present in the entire 30,522 unique words list, somewhere maybe in the 10th word or 100th word or 1000th word, right? Somewhere there will be, somewhere this word will be present. So assume the word this is present somewhere here, 2222. Okay, this is just an example. So assume these are the positions of the input tokens. This is a generative AI course, right? So that is, the token ID can be anything between 1 to 30,522. So just assume the position of the word this is 2222, and the position of is 300, position of A is 987, and the position of the word generative is 1001, and the position of the word AI is 586, and the position of the token codes is 898. Okay, so that is how we represented each token with a token ID. In real time, we will not have just one sentence, right? We may have multiple sentences as well as the input data. So how does the LLM know the starting and ending of the input, right? Input can have multiple sentences too. So how will the LLM know when we have multiple sentences, and what is the starting sequence and what is the ending sequence of the input, right? So that is why we will take special tokens. Okay, so here we are trying to add special tokens for our input. As a human, we can understand the period at the end of the sentence says it's end of the sentence, right? But how will the model understand that the sentence ended? That's why we are adding these special tokens. Okay, so if you notice here, we added CLS as a starting special token and SCP as the ending special token. So CLS means classification. This is input starting and SEP means separated. This means input ending. And assume this is how it looks after adding special tokens. And you may have some question. For example, let's say if any of these words are not present in the 30,522 vocabulary list, right? Then what happens? The LLM is intelligent enough to understand other related words. For example, happiness and unhappiness, right? So if happiness is present in the list, whereas if unhappiness is not there, the LLM will be intelligent enough to understand the related words, and then it will get the token ID of happiness, right? So why are we adding these tokens? Because the model can understand only numbers, right? So what did we do so far? We represented our input as tokens and we added these special tokens as well, right? And the next step is to convert our input tokens into embeddings, right? So this is our input and we are trying to convert into input embeddings. And these embeddings are generated using ANN, artificial neural network architecture. So we use feed forward back propagation network to generate these embeddings. We will pass the entire input tokens and we will get the embeddings for every single token. Okay. Since we are using BERT as an encoder model here to explain this architecture, and each model will generate a fixed dimensional embeddings for each token. In case of BERT, it generates 768 dimensional embeddings for each token. So 102 will have 768 dimensional embeddings and 2222 will have 768 embeddings. Similarly 300, 987 and all the way to 6005. Each one will be represented as a 768 dimensional embeddings. So that is what will happen once the input is converted to input embeddings. And we have total 8 tokens. So we will have total 8 embeddings with a vector size of 768. Right? That is, every embedding will be of size 768 dimension. So now what we did, we converted the text into embeddings of size 768 dimensions. And if you notice here, these word embeddings, they are not random numbers, right? They are arranged in such a manner that similar words will come closer together. Okay, that is, in 768 dimensional space, it's trying to arrange all the 30,522 words that have contextual meaning, right? Since we cannot imagine 768 dimensional space, for example, let's take only 3-dimensional diagram so we can visualize, as we cannot visualize 768 dimensions, right? If you notice here, we have sky, machine and wings, drone, airplane and eagle, right? So if you take here, this word drone is very close to sky, wings and machine, because drone has wings and drone is a machine and drone can fly in the sky. So this word has a contextual meaning. That is how the close words are trying to stay together, right? Similarly, if you take eagle, this is very close to sky and wings. Eagle can fly in sky and it has wings, but eagle is not a machine, right? Similarly, let's assume if you have ostrich here, ostrich is very close to wings and sky, but ostrich will be very far away to machine because ostrich is not a machine. So these word embeddings represent which words are together out of the 30,522 unique vocabulary list, right? So now we understand these embeddings. So for every single token we have 768 dimensional representations. Now let's see the architecture diagram. We have input and we converted that to input embeddings with a vector size of 768. And now if you see the diagram, next thing what we are doing here, we are trying to add positional encoding to the input embedding. You see the addition operator here. So we got 768 vector size of input embeddings, and next thing is we have to identify how to find positional encoding and then we can add these two. So now let's see what is positional encoding. So as a human, we understand the position or context of each word with respect to each other word. right, in the input sequence. But how will the model understand the position of each word with respect to each other word? So to understand the context of a word, the order of the word is important, right? So which order the word belongs to in the input sequence. And to understand the order of the word, we have to add a technique called positional encoding. So the objective of positional encoding is to add position information of each word. But how can we do that? So maybe you can try to add an index to each token, like 0, 1, 2, 3, 4, 5, 6, 7, etc. But this is just one sentence, right? In real time, we will have petabytes of data, right? So this indexing may not be a good idea, right? So what else we can do to add position information to each word or token? We need some function which can generate a continuous index or continuous number, right? That is, 0th index stands for CLS, the first index stands for this, and second index stands for is, etc., right? And if the index repeats, then we will be confused, right? So the index should not be repeated and each token should have a unique index, right? So we need some continuous unique numbering system, right? So if you use index, it may not work, because if you have huge amounts of data, then this indexing might not work. So the solution they have given is to use sine and cosine functions to generate these positional encoding. That is, continuous unique numbering systems can be generated by using sine and cosine functions, right? And you can refer this if you want to deep dive. I found this very useful. In this they explained using GPT, so you will see 512 dimension, right? But we are using BERT, so which is 768 dimensional. So let's go to the positional encoding. Right? So what is positional encoding? So with the positional encoding, the model not only knows the context of the word, and it also understands the position information of the word. So what is positional encoding? We want each word to carry some information about its position in the sentence, right? In the input sentence. And we want the model to treat words that appear close to each other as close and words that are distant as distant, like we saw in the other example, right? And we want the positional encoding to represent a pattern that can be learned by the model, right? In our example, as you can see, the word AI is very close to the word course. And similarly, the word this is very distant to the word course, right? Here you can see the input sequence is your cat is a lovely cat. So that is the original sentence, and they are trying to apply positional encoding here. So here they are using GPT, so that's why you are seeing 0 to 511, because each model will have fixed vector size, right? So that is how we are trying to get the positional encoding by using sine and cosine trigonometric functions. But you might think, like, why we need trigonometric functions? Because sine and cosine functions can generate continuous numbers, right? Because these trigonometric functions like sine and cosine naturally represent a pattern that the model can recognize as continuous. So relative positions are easier to see for the model, right? So this is how it can generate the continuous pattern. And if you notice here, we only have a vector size of 4, right? This is not 512. So let's take the simple example so it will be easy to understand, right? So these are the formulas. This is position encoding, PE, of, you'll have to pass position comma 2i. So I is the index, right? Equal to sine of position divided by 10,000 to the power of 2i divided by d model. That is the dimension of the model. Here we are taking d as only 4, right? If it is BERT, you already know it is 768, whereas if it is GPT, you know it is 512. So each model will have fixed d, that is embedding vector size, right? This is how we'll calculate positional encodings by using sine and cosine functions. Here POS means position of the word, and I is nothing but either sine of 0 or cosine of 0. So you can see sine and cosine, and again for the first index sine and cosine, right? So for each index 0 and 1, we'll do sine cosine, right? This is how we'll calculate the positional encoding. Here sine and cosine as a pair we are trying to calculate for each embedding. Let's assume for position 0, right? So this is position 0, position 1, position 2 and position 3, and the I value 0, 1, 2, 3, right? So you have to replace for the first position, so that is 0. So you have to replace with 0, and the value of I is here 0, and again 0 here, value of I is 0. This is sine cosine, one pair. You calculated sine cosine at the 0th index, and the next one is sine cosine at the first index, right? So the index value will change. So that is how we calculate positional encoding. So similarly, if you have a dimension of 768, so you will see a pair of sine cosine, right? So total it will be 768 divided by 2, right? So that many pairs you will see sine cosines, right? So that is how you will calculate the positional encoding. And now let's go to this diagram again, and the next step is, once we have positional encoding, we are trying to add this positional encoding with the input embedding. So finally we will get embeddings along with the positional encoding, right? Now with this positional encoding, the model knows the position of each word and which word comes closer to each other word, right? So is AI is closer to coarse word, or AI is closer to this, or AI is distant to the word this, right? So with this position encoding, the model is now intelligent enough to understand the position of each word and which word come closer to each other word. But is this sufficient? We also need to know how each word is related to each other word, right? So that is the correlation, right? That is the relationship between each word with respect to each other word. How this is related to ease, how this is related to a, how this is related to generative, how the word this is related to AI, or how the word this is related to course. So similarly, ease is related to this, etc., right? So each word, what is the relationship of each word with respect to each other word, right? For example, instead of this is a generative AI course, let's assume we took this input sequence as the input to our model, right? The girl is running, she is going to school, she eats apple every day, she has an Apple phone, right? So even after using positional encoding, the model still doesn't know the context of a word in a sentence, right? If you see here, how does the model know that she refers to girl, right? As a human, we know the girl is running, she is going to school. So we know she refers to girl, but how will the model know? And also, if you see in the second sentence, one apple refers to fruit, right? And the another apple refers to Apple phone. So same word apple with different meanings, right? So how will the model understand? To make the model understand, we have a concept called attention, right? So that is the main reason why the artificial intelligence is very popular, because of the attention concept. So attention means trying to understand every word with respect to each other word in the input sequence, okay? So the whole objective is, for every word we will calculate attention, and all the values that the attention generates will be between 0 to 1, because that is a probability, right? So positional encoding is to add position information, that is the order of the word, right? The objective of attention is how every word is related to every other word in the input sequence. This is just one sentence, but if you take these sentences, the model will get confused. The model cannot understand that she refers to a girl, or apple refers to fruit here, and apple refers to a Apple phone here, right? So that is why we need to understand the relationship between each word with respect to each other word. So the objective of attention is how every word is related to every other word. So that's how we are preserving the context, right? And this attentional calculation is computationally expensive, right? But let's try to understand how we'll calculate the attention, right? So like I said, the attention score will be between 0 to 1, and which word has the highest attention score, that will indicate the relationship between those two words, right? So now let's see how to calculate attention, right? So we have query matrix Q and key matrix K and V, that is a value matrix, right? So we have three here in this formula. For example, let's try to calculate attention for the word this, right? So like I said, we have query matrix, key matrix and value matrix, right? So embeddings plus positional encoding of word this will be multiplied with query matrix, then we'll get query vector. And similarly, embeddings plus positional encoding of the word this will be multiplied with key matrix, then we will get key vector. And similarly, embeddings plus positional encoding of the word this will be multiplied with value matrix, then we will get value vector. And the attention score is query matrix multiplied by transpose of key matrix divided by dk, and we'll multiply this with value vector and we'll pass it to softmax, and this softmax is for normalization. So if you get the big value, we'll try to normalize using softmax, right? So that is how you will get the value between 0 to 1 as an attention score. So this is the formula for attention score. So now you know the transformer is powerful because of the attention concept, right? And the query matrix, key matrix and value matrix, these are fixed for each model, right? So all words query matrix, key matrix and value matrix will be the same, so they are fixed for each model. And the matrix values are calculated using neural networks, so that is out of the syllabus here. And then we will apply this softmax, so we will always get a value between 0 to 1. Go back to this article that we were referring before. Let's go to the self-attention section. So here you can see what is self-attention, and this is the formula they are trying to apply. And the input sequence is your cat is a lovely cat. So here we are trying to calculate the attention score for each word with respect to each other word. That is how the word your is related to the word your, how your is related to cat, how your is related to is, how the word your is related to a, each word with respect to each other word, how your is related to every other word in the input sequence. And if you see here, so let me zoom so you can see, and if you notice here, it is 0 0.2, 0 0.1, 0 0.1, 0 0.1, 0 0.1 and 0 0.1, right? That is how we are trying to understand how each word is related to each other word in the input sequence. Whatever the word has the highest attention score, then those two words will be closely related in the input sequence, right? And if you notice here, if you add the attention score row wise, then you will get the value of 1, right? Now let's see how to compute self attention, right? And if you notice here, this is of size 6 by 6, right? And they are using GPT model, that's why the vector dimension is 512. We are doing query times transpose of key matrix, so that is why we are getting the 6 will cancel and 6 by 512. So by using this attention score, this will solve one word multiple value problem, right? That is apple is a fruit or apple is a phone, right? So you can easily understand the relationship between each word with respect to each other word. And once you have the attention score, the next step is we're trying to add and do the normalization, right? So we are normalizing by using softmax here, right? So that is how you can calculate the attention score and solve this problem whether apple is a fruit or apple is a phone. So attention is all you need. And if you want to deep dive on attention, this is the paper. Let me take you there. Attention is all you need, right? So this is the paper. You can deep dive if you are more interested on how we are calculating the attention score, right? But the objective of attention is trying to understand the relationship with each word with respect to each other word in the input sequence. So that is how it generates or predicts the next word in the sequence, right? And without attention score, these models cannot predict the next word, right? So meaning it generates the nearest probability or related word, right? And let me ask you a question here. In this, she eats apple every day. She has an Apple phone, right? So the token ID of apple, is it the same or different? So if you notice here, the word apple will have the same token ID, right? Out of 30,622 unique vocabulary list, the word apple will have the same token, but the positional encoding will be different, right? It will be different for the word apple here, and the positional encoding for the apple is different, right? But the token ID will be the same. And how will the model understand one is fruit and the other one is phone? Because of the concept of attention, right? Alright, so we saw once we pass the input sequence, how we are generating the input embeddings, how we are generating the positional encoding, and once we add, we are getting input embeddings with positional encoding. And then we saw attention, and we understood how to calculate the attention score and how to normalize it by using softmax. Right, so that is what is encoder part, and in the coming lecture we will see decoder side as well. Alright, thank you. Now let's summarize what we learned in the previous lecture, and then we will deep dive into the decoder side as well. So once you know the transformer architecture, you will know which model you need to pick depending on your requirement, whether you have to pick encoder model or decoder model or encoder decoder both, right? For example, let's say you're trying to perform different tasks, right? NLP, that is natural language processing. NLP is a computer science field that enables computers to understand and use human language, right? NLP has many applications. For example, let's consider sentiment classification, right? This is a supervised problem, and in sentiment classification we will pass the input to the model. That is, you have a bunch of text and you want to classify that text into groups, right? And you want to predict whether it is a positive sentiment or negative sentiment, and you know the actual value, right? So you can calculate the loss and retain the model accordingly until the model understands the pattern. So here you can just use the encoder model itself, right? Because you are not generating anything here. All you're trying to do is just trying to classify whether it is a positive sentiment or a negative sentiment, right? So in this case, you don't really need a decoder model. All you need is just the encoder model itself. For example, you can use BERT as it is a encoder model, right? And another example is NER, means named entity recognition, right? So by using this, you can identify what is the organization name, what is the date present, or location present, or all the people present in that organization, etc., right? So you can try to extract from the text, right? So you can just use encoder model here. You do not need decoder because you are not generating anything. All you are trying to do is you are just trying to extract from the input text, right? And the another example is text summarization, right? So let's assume you have a long test. For example, companies 10K report, right? 10K report means comprehensive overview of a public company's business, financial condition, and results of operations, including audited financial statements, right? So all this information will be present in the company's 10K report. And let's say you just joined a company and you want to review the 10K report, right? And it's overwhelming to go through the long report, right? So in this case, you can just summarize and go through quickly by using this text summarization model, right? So you can just use the encoder model here because you are not trying to generate anything. All you're trying to do is just you are trying to summarize the text, right? So you don't need decoder here. You can just use encoder model and summarize your long text. And the next example is text generation, right? So given a context, you want to generate the next token or word, right? So you're trying to generate something. So you need decoder model, for example, GPT. And the next example is relationship extraction. For example, let's say you have two companies. Company ABC acquired company XYZ, right? So here the relationship is acquired. So you can represent the relationship and create a knowledge graph for the better understanding of the relationship between ABC and XYZ companies, right? So you can go through the relationship extraction and you can quickly prepare a report, right? So in this case, you are not trying to generate anything. You're just trying to understand the relationship between two entities. So you can just use encoder model here because you are not generating anything, right? And the next example is language translation, right? So for example, let's say you're trying to translate from English to Spanish, right? In this case, we need both encoder and decoder. That is, one focuses on the source, that is English. The other one focus on the target, that is Spanish, right? So we need both encoder and decoder, but we will deep dive into this. So we will understand both encoder and decoder, right? So now you know BERT is an encoder model which is good for classification or sentiment analysis or NER tasks, right? Whereas GPT, that is a decoder model, when you want to translate some language or generate something, right, then you go for GPT. And if you are just trying to classify instead of generating, you don't really need GPT, right? You can just use BERT. So once you know the transformer architecture, right, that is both encoder and decoder, then for what kind of application you will know what kind of model, that is encoder or encoder decoder models to use. You can save cost and improve the accuracy because you know which model works best for what kind of application, right? For example, let's take an application which requires both encoder and decoder, so we can learn both encoder and decoder side, right? So let me take you to this article. I found this is very helpful. So this is the article by J. Alamar, right? So first let me explain at a high level, then we will deep dive. So here if you notice, we are passing Spanish input to the transformer and we are trying to get the output in English, that is Spanish to English translation. So we need both encoder and decoder in order to do this task, right? All we are trying to do is we are trying to do the language translation here, right? So once you pass this Spanish words to the transformer, then what happens? It goes to the encoder model, right? So what happens here? You will pass the Spanish sentence to the model as the input, right? And then you know the flow. Every sentence will be tokenized and every token will have a number, right? That is the token ID. And then we will add the special characters CLS and SCP, right? Classification and separator that will be appended to the tokens, and then you will get the embeddings here. And then the next step is we will calculate the positional encoding, and then we will add both embeddings and positional encoding. Then you will get the embeddings with positional encoding, right? And after this, self-attention mechanism, right? So attention will give you the context, that is the relationship of every word with respect to every other word. And then we will use softmax to normalize, and then we will get a number between 0 to 1. So that is the attention score, right? Then that self-attention will be passed to ANN, right? This is the feed forward network, and you will get self-attention. Then again we will pass to ANN, and we will repeat this step 6 times. As you can see in the diagram, we will pass 6 times to these encoders, right? So what is the encoder output after passing 6 times? The final output is Spanish word attention, right? That is the model knows every word versus every other word relationship between those Spanish words, and every Spanish word context has been captured by this encoder. So the encoder understood the complete input Spanish sequence. So what happens next? So now the next step is decoder flow, right? So in the decoder, the first input, that is the start, that will be passed. The start is a special sequence, okay? And then again the same flow. Again we will apply the embeddings, and then we will convert start into embeddings. So start is the starting sequence to the decoder model, that will be converted to embeddings, and then we will calculate the positional encoding, and then we will add both embeddings with the positional encoding. Then we will get embeddings with the positional encoding for the starting sequence only, and then we will apply masked self-attention. So this is the only difference when compared to encoder. In encoder we have self-attention, here it is masked self-attention, right? But the rest of the steps are the same between both encoder and decoder. And we will use key vector K, value vector V from encoder model, and we will use query vector from decoder masked self-attention, right? So decoder only works with target, that is English, right? And because of the encoder decoder attention, so if you see here, in encoder we have self-attention and feed forward, and in decoder we have self-attention, feed forward. You see the additional one here, encoder decoder attention. So because of this encoder decoder attention, the model understands that the word J in Spanish is related to the word I, okay? So J is related to the word I, Sus is related to the word yam, right? So that is how the model understands the relationship between Spanish and English because of the encoder decoder attention. And in encoder, the model understands Spanish word versus every other Spanish word context relationship, right? And in decoder, it predicts J means I, right? So that is, this J is related to the word I, Spanish to English, right? Then in the next step, so first we passed start as the input sequence, and then it predicted J means I, and then both predicted values I and start, that is the starting sequence, will be again passed to decoder model. Again the process repeats, right? And again it will calculate the embeddings, and then again positional encoding, and then masked self-attention. Then the next word will be predicted, right? So what is the next word? Yam. Then I am, and then the starting sequence, right? these three will be passed again to the decoder model. Again the process repeats: embeddings, positional encoding, masked self-attention, then the next word will be predicted, right? So at a time the decoder is trying to generate the next word, only one word, it's actually one token at a time, right? And the process will stop once it sees the special token SCP at the end of the sentence, right? So depending on the task that you are trying to work on, you need to pick either encoder or encoder decoder model, right? For example, for language translation we used both encoder and decoder, and whereas in classification you just need encoder itself, you don't need decoder because you're not trying to generate anything. And in case of NER, just encoder is enough because you're not trying to generate anything, so you don't need decoder. And when you're trying to predict the text, right, you're trying to generate something, in that case you need GPT, you don't need encoder, right? So now you understood the difference between encoder and decoder at a high level, right? That is, in case of encoder it is self-attention, right? Whereas in case of decoder it is masked self-attention. So now you understood the difference between encoder and decoder models, right? At a high level, in encoder it is self-attention, whereas in decoder it is masked self-attention. Okay, so that is the only difference, and remaining all the steps are almost the same. Now let's go back to this article and deep dive. So what we did first, we passed the Spanish input to the transformer to translate this Spanish into English, right? So that is our intent. And the next step is we have encoder and decoder, right? So inside the transformer we have both encoder and decoder. And again, if you deep dive, we have 6 encoders and 6 decoders, right? The more and more encoders you will repeat, the better patterns you can identify, right? So that's the only objective of why we are repeating here. And if you deep dive more, in encoder we have self-attention and feed forward neural network. This is ANN, right? And if you deep dive more, in every encoder we have self-attention and feed forward, that is ANN, artificial neural network. And encoder focus only on the input, that is Spanish, and decoder always focus on the target, that is English, right? And in decoder we have 3 things: self-attention, encoder decoder attention, and feed forward, right? We have this extra thing, encoder decoder attention. So this will give how the Spanish word is related to English word, right? And if you want to see the code, let me show code as well. So if you go to this GitHub URL, right, here they have provided the code for translating from English to German, right, with a pre-trained model. So if you are interested, you can deep dive and look into this code as well. And if you want to see visually, right, so here you have the code as well, and you can also see the visual part, right? So if you see here in the attention, you have input input, input output, and output output, right? So input input means encoder self-attention, right? That is each word with respect to each other word. That is the relationship between each English word with respect to each other English word. That is input input, which is encoder. And input output means encoder decoder self-attention, that is English to German, right? So this will help how each word in encoder relates to each other word in the decoder, right? And the next attention is output output, right? So output output means decoder self-attention, right? That is German to German, every word in German to each other word in German, right? So whichever word has the highest attention score, that will be predicted as the next word in the sequence, right? Now let's go back to this article so we can deep dive. So now let's understand the input, right? So each word may be split into multiple tokens, right? So not just one word to one token, right? But just to keep it simple, let's assume this one word is converted to one token, right? Just for understanding. So this is the input text that will be converted to tokens, and then we will get the token ID, right? And then what happens? The next step is self-attention, right? That is, it will try to understand the relationship between each word with respect to each other word in the input sequence. That is J with respect to J, Sus, Etudient, right? Similarly, Sus with respect to Sus, J, Etudient, right? And then Etudient with respect to Etudient, J, and Sus, like we saw in this example, right? So it will try to understand each word with respect to each other word in the input sequence. Then that will be passed to ANN, that is feed forward network, and you will get the self attention. And you know the self attention is matrix multiplication, right? And what happens next? And we will pass that to 6 encoders, right? That is output of encoder 1 will be passed to encoder 2, and encoder 2 output will be passed to encoder 3, etc. And then similarly output of encoder 5 will be passed to encoder 6, right? So that is how we'll calculate the self attention. And if you notice self attention at a high level, the objective of self attention is which word is closely related to which other word in the input sequence, right? So if you see the sequence here, the animal didn't cross the street because it was too tired, right? So it is trying to understand the relationship of each word with respect to each other word, right? So that is the objective of self attention. And if you notice here, we have query matrix that will be calculated again using ANN, right? And key matrix and value matrix as well. So if we deep dive, we have 2 by 4, right? This 2 by 4 times this is 4 by 3, and then you will get 2 by 3, right? 2 by 3, this is the matrix multiplication, right? So you will get query vector. This query vector contains input, embeddings plus positional encoding. And similarly, this is the input sequence, and then this is the key matrix. We will do the matrix multiplication and we will get the key vector. And this is the input sequence, and this is the value matrix. We will do the matrix multiplication and we'll get the value vector. And then how to get the self attention? So we will matrix multiply query vector and transpose of key vector, right? And then we will multiply with the value vector as well. That's how we will get the self attention, right? This entire thing is just for one head, right? And if you want to see the entire process, you can see here. So first we are trying to pass the input, and then next thing is we are generating the embeddings, and then we'll get the query key and value vectors, right? When we multiply input embeddings with query key and value matrix, right? And then we'll get the attention score. Here in this paper they're trying to divide it by 8, then softmax, then multiply value with that, and then we'll get Z1 and Z2. These two are the self attention score, right? So we did this for one head. This paper says we need to do for 8 times, right? So that is for the multi-head. And then we will calculate all the attention scores, Z0, Z1, so on, Z7. This is for the multi-head. This is how we will calculate. It is a multi-dimensional array, right? We will flatten by multiplying with all the weights W0 and pass it to ANN, because ANN allows only vector form but not the matrix form, right? So that is how we'll calculate the final attention for the multi-head. So we are learning the architecture of the transformer behind the LLM, right? But in generative AI, we are not building an LLM, right? But for your understanding how the LLM functions behind the scene, we are trying to understand the transformer architecture, okay? If you are interested, you can build an LLM once you know the architecture, right? Because you already have the code as well. But you need two things, right? So the number one is you need data to train the model, and the number two is GPU to process the data. And there will be a lot of CO2 emission as well, right? Carbon dioxide emission during this training process, right? And you also need to be careful with ethical AI, right? Let me show an example. So if you see this article, right? So a college student in Michigan received a threatening response during a chat with Google AI's chatbot Gemini, right? So what it sent, this is for you human, you and only you. You are not special, you are not important, and you are not needed. You are a waste of time and resources. You are a burden on society. You are a drain on the earth. You are a blind on the landscape. You are a stain on the universe. Please die. Please, right? So you also have to be careful when you're trying to build any models, right? And in real time, it is not just transformers, right? We will also have reinforcement as well. That is, if you see the gaming applications, they use reinforcement architecture, right? Now let's understand the decoder side as well. So far we saw encoder. Now let's deep dive decoder side as well. So this is the decoder side. So here what we're trying to do, we need to translate the input words thinking and machines, right? So this input to the decoder is, we will pass the starting sequence and we'll get the token ID, and then we'll do the positional encoding, right? Similar to how we did before for the encoder model. And then we will apply the self-attention. That is, in step number 1, there is only the starting sequence. So it calculates the self-attention for only starting sequence in the decoder, right? So if you notice the diagram here, from the encoder, we will take the key and value vector, and from the decoder, we will take the query vector, and we will do the encoder's decoder attention, right? And this output of decoder along with the starting sequence will be fed again to the decoder model, right? So let's see the visual diagram so it will be clear for you. Let's see the decoder time steps here, right? So first, the starting sequence will be passed to the decoder model, and then it will try to predict the first word, that is I. So we are taking key and value from the encoder and query from this decoder and trying to predict the next word, that is I, right? And in the second step, it predicted am. And then again what happens, the previous outputs, the starting sequence I am will be passed again, it will predict A. And then again I am A, it will be passed to this, and then it will predict student. And then again starting sequence I am a student will be passed again, and then it will go to the end of the sequence and it will stop generating, right? So the encoder knows the relationship or context between input sequence words, right? These are the Spanish words. And decoder knows the relationship or context of the target, only one word at a time, right? And with encoder decoder cross attention, right? That is how the model knows the relationship between J means I, sus, right? So that is how it will identify the relationship between Spanish and English word. That's how the model is able to predict and generate the output, right? Remember, only one word at a time, right? That is, it's actually one token at a time it is trying to predict, not the entire sequence in one go, right? It is only one word or one token at a time, right? So far we saw an example of both encoder decoder, right? Encoder decoder transformer architecture with a language translation example. Now I have another article that shows only decoder model. So let me take you here so we can see only decoder part of it, right? If you see here, why do you need this masked self-attention in the decoder? Because the decoder only knows the attention score of only the starting sequence in step number 1, and remaining all will be masked. And in step number 2, we will pass starting sequence and the predicted word, and then it will know the score of the starting sequence and robo, right? And remaining all will be masked, right? So it only predict the starting sequence and the remaining all will be masked with infinite. And in this next step, starting sequence and the first word and the remaining all will be masked. Starting sequence, the remaining 2 predictions, and the remaining will be masked. So that is how we are doing the masked self-attention, right? It only knows the score of this and the previous words, and the remaining all will be masked, right? Here we are setting to infinite because the soft max of infinite is 0. Right? This is the only difference between encoder and decoder. One is self-attention, the other one is masked self-attention, right? So now let's go back to that article so we can deep dive. This is a nice decoder example, right? So first thing is we are passing the starting sequence. In step number 1, it only predicts the, only one word. And in the next step, what happens? We are passing again starting sequence and the predicted word, that is the, to the decoder model, and it predicts thing. And then again in step number 3, we will pass starting sequence, the, and the predicted word thing, and then it will predict the next word, right? And so on. So one word at a time, right? Or one token at a time actually. That is how the decoder predicts. Alright. So now let me ask you a question here. So what is the difference between BERT, encoder, and GPT? Decoder models, right? So BERT means that is an encoder model. In encoder model, every word knows the context of every other word. That is, it is bidirectional. Whereas in GPT, that is a decoder model, it only knows the previous word's context in order to predict the next word, right? Because the remaining all scores will be masked. It only knows that word score and the previous scores, so it can predict the next word, right? So that is the only difference between encoder and decoder based models. So now you know both encoder and decoder side of the transformer architecture, right? And which model to use to solve what kind of problems, right? So that is the whole architecture of transformer. All right, thank you.